Let's first start with a brief history of fireworks. Fireworks were created in China during the 7th century where they were used in combat to scare opponents. Now we'll go into the basics of fireworks. These are some of the common reactions associated with the explosions of fireworks. As is evident, a nitrate is used in both of the reactions, along with sulfur and carbon. We'll go into detail very shortly. There are three basic elements that a firework is composed of. They are oxidizing agents, reducing agents, and binders. First, let's talk about the oxidizing agent. This is the agent that produces oxygen gas, which will eventually be used during the combustion process. The oxidizing agent is used in a decomposition reaction, and is often a nitrate, chlorate, or perchlorate. Here are some of the decomposition reactions that take place in common fireworks. The first one is a decomposition of potassium nitrate, which produces potassium nitrite and oxygen gas when heat is added. The next reaction is the decomposition of potassium chlorate. The products of this reaction are potassium chloride and oxygen gas. The final reaction is the decomposition of potassium perchlorate. The products of this reaction are potassium chloride and oxygen gas as well. As you can see, all three of the reactants for these decomposition reactions are similar in their molecular geometry. Each has a negatively charged oxygen atom that can attract a positively charged potassium ion. So why are these reactants so good at what they do? This comes down to their ability to decompose. All are very soluble in water, and similarly, with regards to fireworks, all are capable of decomposing and yielding oxygen gas.
The next component of a firework is the reducing agent. It is the agent that provides fuel used in the combustion of the oxygen gas produced by the oxidizing agent. The fuel reacts with the oxidizing agent to create a hot gas. This gas then expands, which leads to an explosion. Charcoal and sulfur are usually the reducing agents in a firework. The sulfur in black powder intensifies and continues the reaction between the other two ingredients, as a reducing agent is also what regulates the speed of a reaction and separates a firework from a bomb. Here are the common oxidation reactions of the reducing agents in fireworks. In the first picture, we see how an oxidation-reduction reaction works. One atom gains electrons, while another loses them. The next two pictures summarize what is going on during the oxidation process of carbon from charcoal and sulfur. Carbon's oxidation state goes from 0 to +4. The same is the case for the sulfur. The final part of a firework is the binder. Similar to a binder which holds your homework and classwork, the binder in fireworks holds the oxidizing and reducing agents together, along with other chemicals. Just like your binder sometimes makes it hard to remove papers easily, a binder in a firework makes it harder for all the chemicals to react at once, as their concentrations are decreased when additional substances, such as a binder, are added. The different forms of dextrin, a starch/sugar, are often used as a binder. The one we used in our fireworks was cornstarch. In this picture, what you see is dextrin. As you probably know, not all fireworks are the same color. This is because they have different substances in them. For example, calcium salts produce orange fireworks, sodium compounds produce yellow fireworks, strontium or lithium salts and carbonates produce red fireworks, and barium salts produce green fireworks.
So how exactly are colors produced? Let me explain. When an electron is in an excited state, as it is when the firework is burning, it is an orbital with high energy. However, once the atom leaves the firework, it is no longer on the burning substance. As such, the electron must go back to the ground state. The ground state has much lower energy than an excited state, so in transitioning, the energy has to go somewhere. When an electron goes from an excited state to a ground state, energy is lost. When a quantized amount of energy is lost, it is lost in the form of light. Light is emitted. Different elements allow their electrons to have different amounts of energy, so when a different amount of energy is emitted, there is a different frequency, thus causing a different color of light.